Okay, let's get started. It's my pleasure to introduce Dan Weld. He's a professor at the University of Washington. He's a member of our scientific advisory board, but more importantly, he's one of the leading thinkers and researchers in AI for a long time. He's been called many times the father of modern planning. Most of those times it was by me, but still. It's a genuine honor. He's a fellow of AAAI, of ACM, and here's a talk on another leading school of thought in AI that he's creating and evangelizing. So Dan, please.
Thank you. Okay, so I want to talk about making intelligence intelligible rather than just plain smart. And the basic motivation for this is because AI is being adopted everywhere, deployed in many mission-critical systems. And oftentimes the performance is really good, but not always, right? Sometimes it's erratic. And in particular, when you're trying to actually have this be deployed, or if you're trying to have an AI system that's being worked in concert with a human, sort of a human AI team, if you've got this bizarre, unintelligible behavior, it can lead to poor team performance. Some people say intelligibility, who needs that? But I'd like to argue that yes, we do need it. And just as an example, I think this is going to be familiar to many of you. Excuse me for promoting Microsoft's question answering system here rather than yours, but I think they behave quite similarly. So as you guys know, we can take a squad question and ask a question like who asked Luther to disavow his writings. And I don't know how many people have seen this particular squad question before. People know what squad is? People have the answer. Weld, BIDAF, and Microsoft get this one right. But if you give it a similar question, like this one, the same model thinks the answer is Alice. Okay, so I think that's pretty bizarre behavior, because if we can get the Pope on the previous question, you'd think that simple questions would do much better. So why is the system getting this one wrong? Well, I think there's lots of reasons. So AI methods are based on these complex nonlinear models. They're trained via some complicated optimization problem, and they search vast search spaces, and so it's really hard to know what the heck they're doing. But the key questions I'd like to argue are, one, when can we trust the AI system? And two, more importantly, how do we adjust the AI system? So what I want to do in the talk is, first of all, try to catalog the reasons for why intelligibility is important. And then I'm going to back up a little bit and explain what exactly I mean by intelligibility, talk about intelligibility mappings, making it interactive, talk not just about intelligible machine learning, but also search, and then ending up about maintaining trust. So as you can tell, this is a talk. I haven't quite given this version before. Here are the reasons for intelligibility. The missing reason, which should be 1A, or what I was hoping would be 2, is the fact that features might be missing. But I'm going to go through each one of these in turn. I think this decomposition of the reasons is actually one of the most interesting parts of the talk. So the first one that we want our system to be intelligible is because the optimization that the AI is doing, it may be the wrong thing. It may be what we think the system should be optimizing, but not really the right thing. So if we're trying to build a machine learning system that does HR in a modern corporation, there's like many different factors that we want to take into account, and it's not clear that we've been able to specify the objective function correctly, where how do we trade off diversity from job performance and ethical recruiting practices and so on. And of course, lots of people have talked about examples like, suppose we build an AI system and ask it to maximize paperclip production, and the things that could go wrong if we've given it a simple goal like that. The second reason is because the AI, if it's a machine learning system, is using the wrong features. And I can't really explain this to you right now, but I'll come back to this reason in a minute. The third reason for wanting your system to be intelligible is because of distributional drift. So the system may perform really well in the training distribution, your test distribution, but once you deploy it, the distribution oftentimes changes. And especially if you've got humans in the loop with the AI system, whether it's a team setting or social media feeds or advertising where you've got an adversarial situation, oftentimes the distribution changes quite dramatically. The fourth reason is because explanations make it much, much easier for humans to control the AI system. So in particular, good explanations are actionable. And here is an example from the Google News feed on Android. It's a little bit small, so let me just zoom in to this particular part here. And you can see that Google has told you why you're seeing this story. And it's an actionable explanation in the sense that you can basically explain that actually these parts of the reason were why you didn't want to see the story, and it allows you to update the system's behavior. So it lets you manage preferences. So similarly, why did this end up in my spam folder? It's going to let you change that behavior. Or why did you fly me through Chicago? You can say, well, actually, it's true. I do prefer flying on United, but not when it has me going through Chicago in the wintertime. So in general, this business about enabling control, I think, is really motivated by the notion that many times in the future, and going forward, we're going to see more and more systems where you've got human AI teams. And humans make a set of errors. AI system may actually make some fewer errors than the person, but oftentimes they make different errors. And if we have a system which is intelligible, then we come up with better teamwork. So that's going to allow us to make only the errors that are in the intersection of those two reasons, because the human's going to be able to understand why the system is making other mistakes. The fifth reason is because users like intelligibility. Even if they're not going to control the system, a lot of psychological studies have showed they're just going to like your system better if it gives you an explanation. The sixth reason is because oftentimes many times people focus on this idea of machine learning to automate a task, and that's important, but oftentimes that's not the only use for machine learning. Sometimes we actually want to get insight out of things. If it's an unintelligible model, you don't get any insight. It doesn't actually allow human beings to learn. So we want, in many cases, models people can learn from too. And then the final reason is a legal one. Yeah.
Can I interject something? Mm-hmm. So if you go to number 5, number 4, they were going by so fast. I think that you're perhaps a little bit overstating the win, because I think implicit in what you're saying is that the human is rational and can understand the intelligible explanation, whereas they might be mistaken, or can accept the intelligible explanation and so detect the AI-specific errors. But for example, it's entirely possible that the AI system would convince the person to adopt something that's wrong, or even worse, that the AI system will be right, but the person, due to their own biases, preconceptions, etc., will choose to ignore the system. So it's not, even if you have, quote, perfect communication between the partners, it's not necessarily that the whole is greater than the sum of the parts.
It is true that I think limiting the errors to this intersection is sort of the best case, and it may well be that the human might override with an explanation, or without an explanation, the human might override the AI when it shouldn't. And similarly, the AI might actually convince somebody of something, and so allow the human to make that thing. But I think that's the best case scenario. But just because you may not get the best case, I think having the explanations allows people to get closer to that intersection. So I think it's a net win. And I think people can build effective models of where the AI system is competent, even in situations where they can't perform the task themselves, and even when the AI system doesn't have such a good model. So I think that and I'll come back to that a little bit later in the talk. So I think it's an aspirational thing to shoot for. Well, maybe I did state it very strongly. Plus, it makes people happier. And then the final reason is because even if you as an AI researcher don't really want to make your algorithm explain itself, if you want to operate in Europe, you might have to provide that kind of functionality. Obviously, that's still being tested legally, but there's other issues. In terms of determining liability, issues like intent and so on become very important, and so knowing exactly what the algorithm is doing and why can be important for legal reasons. Okay, so lots of people write about interpretable models, intelligibility, and so on, and don't actually define the term. Some of the definitions, I think, are overly strong. The definition I'm going to use is, first of all, a relative notion. So it's not like it is intelligible or it's not intelligible. But the key question is, can a human being predict how a change to the model's inputs is going to change the outputs? So basically, it's the ability to answer counterfactual questions. Offline we can argue about why this is a better one than, say, simulation, or being able to simulate the model. It's sort of strictly easier. If you can simulate the model, you can evaluate a counterfactual, but not necessarily the other way around. So here are just a couple examples. So a small decision tree, as long as the primitives are meaningful, then you get something which is interpretable. On the other hand, if you get a really big decision tree, it's not going to be interpretable. You might have a linear model over semantically meaningful primitives that's interpretable. On the other hand, these models somehow oftentimes don't seem to work very well. So we're not super happy with them. Yeah?
You said that big decision trees are interpretable, but under your definition of interpretability, it seems like it isn't. Like from any micro change, I can see exactly where the decision tree will classify it. So really, it seems like that is.
Yeah, as I said, it's a relative notion. I guess I said it a little bit too quickly. Let me just say it's less interpretable because it takes quite a bit more effort on the part of the human being. And I guess I would say, given a neural network, if you allow a human being enough time, they'll be able to predict, they'll be able to simulate the neural network with pencil and paper and figure out what it's going to do. But it's not very interpretable.
But
so
if you tell me to change one of the features in my decision tree, I can tell you exactly what the decision tree will produce, regardless of how large it is. So it seems like that's unrelated to your definition of interpretability.
So I think that the problem of doing the evaluation requires that you go down a path in the decision tree. So the cost of reasoning about the decision tree is sort of logarithmic in the size of the decision tree. So that's a nice thing. But still, if it gets bigger, it becomes harder and harder to do. You don't believe that it gets harder to do as it gets bigger?
So there's also a time with this. Well,
What?
I guess there is anyway, yeah, okay, sure.
I think it's harder to think about a big decision tree. But if you disagree, we can take it offline. And then a final model, which is one that I don't think people have looked at quite as much, is generalized additive models, which are popularized by Rich Caruana. Here's one that predicts the chance of death due to pneumonia for hospital patients. And the model actually has 56 components. So again, as the model gets larger and larger, it becomes harder to reason about. I've shown 3 of the components, and there's a couple interesting things that really let you see exactly what's going to go on. So here, as you increase somebody's age, the chance that they're going to die of pneumonia goes up. So you can evaluate that counterfactual pretty easily. You can also understand, wow, it's actually something weird that's going on here. Right at age 100, the chance goes down. And so that makes you ask certain questions. Is there a problem in the data perhaps? Or maybe it's the case that once somebody gets to be 100, the doctors start working much harder to try to save them. That's actually, I think, what is believed to be the answer here, but nobody really knows. It's kind of interesting. You can also have these pairwise terms in these generalized additive models. So here you see age versus cancer. It actually determined the risk based on the heat map, so it's nonlinear. These 2 terms actually combine in an interesting way. So in general, the older you are, or rather the younger you are, that means the more likely you are to survive not to die of pneumonia. But if you've got cancer and you're young, that's actually really, really bad. And then finally, here's a really interesting one. It says, basically, if you've got asthma, your chance of dying from pneumonia goes down. And since asthma is a respiratory disease, that seems really kind of counterintuitive. And so this is an example where being able to see this part of the model lets one realize that there's something fishy going on. And in fact, what it is in this case is that there's an unmodeled variable which is correlated with asthma, and it's basically time to care. It means patients with asthma tend to see practitioners much more frequently. When they come into the ER, they get seen much more quickly because they've got asthma, and that actually reduces their chance of dying. So if we add in another variable into the model, which is frequently, is seen very quickly by the doctor, or the mean time between visits to the doctor, almost certainly this asthma would start being seen as a risk factor because it would be taken out as this correlated variable. So that gets back to the rain check I gave you earlier about reasons why interpretability is useful, that you realize that something's amiss in your model. Okay, so if you want to make your model intelligible, I think you've basically got two strategies. The first thing to do is to pick an intelligible underlying model, like the generalized additive models. And if you can use that, then you just use it and we're done. And that's great. And the problem is really if that model doesn't work well enough for you, or if you've got too many features. In that case, basically you've got one strategy, and that's to map it to a simpler model, use that simpler model to give you explanations and also controls, and then the person can interact with the simpler model. So why would you want to do this? Well, there's basically two reasons. One is the model itself is too complicated. The other one is that the features are not semantically meaningful. For example, in a computer vision algorithm, the individual pixels don't really have any meaning, and so you can't get good explanations just straight out of the model. So there's a couple different strategies. One thing you can do is you can simplify by currying, basically, which means get an instance-specific explanation, or you can come up with an approximation, or you can do both of those. And then finally, if you've got semantically non-meaningful features, there's really only one that you could do, and that is map to different features. So usually you have to do all of these things if you want to come up with an intelligible model. And this brings us to the central dilemma. So we want to have an understandable model, not one that's unscrutable, but we also want to have an accurate model, not one that's an oversimplification. And any model simplification is a lie, right? So how do you trust your AI system if it's lying to you when it's explaining what it's doing? There's a trade-off here, and we need to navigate that somehow. So one way of thinking about that is if we're going to map into an approximate model, how do we choose which approximate model we should do? What details should we throw down? And we need some desiderata to make that choice. So to make sense of that, we want to look at some of the psychology literature. And one of the key points that they point out is that all explanations are contrastive. So you might say something like, why is P true rather than Q? And this Q is often implicit in the question. Usually we just say, why P? But there's always this foil hiding around someplace. So for example, I can say, Amazon, why did you recommend that I rent Interstellar? And if Amazon might come back and said, well, you've liked other movies by Christopher Nolan, which seems like a pretty good explanation, but it's making an assumption about what the foil is, right? It's assuming rather than, rent some other movie, presumably some other movie not by Christopher Nolan. On the other hand, maybe if a foil was, why did you recommend that I rent Interstellar instead of buying it? This explanation is no good for that question. So any explanation is relative to a foil. Secondly, any explanation is fundamentally a social process. It's a two-way conversation. So in that dialogue, if you get an explanation you don't like, you might want to change the foil. There's a bunch of other dialogue acts you can do as well. I'll come back to that a little bit later. And if you can't show all of the details in your explanation, then it turns out people prefer First of all, details that distinguish between fact and foil, necessary causes over sufficient ones, intentional actions over actions that are taken without deliberation, proximal causes versus distant ones, abnormal causes versus common ones. And there's been psychological studies showing all of these things. Some of the studies are really quite troubling. So they show that people like explanations with fewer conjuncts, regardless of the probability of those conjuncts, regardless of the probability of explanation. They prefer explanations that are consistent with their prior beliefs. And furthermore, even more troubling, and this actually gets back to what Oren said a minute ago, people prefer an explanation even if seeing an explanation makes people want to believe it's true, whether or not the explanation has any sense. And furthermore, if this is an explanation they've seen previously, it strengthens the effect, and they're even more likely to believe it's true. And so what this comes down to is the cognitive biases that Kahneman and Tversky have brought up. There's many, many of them. And I think there's sort of an ethical question. As we're generating these explanations, should we be generating explanations that cause people to believe the explanation is true? Or should we be giving explanations which more match reality? You can imagine optimizing for each one of these things. I'm hoping that we're actually going to be trying to generate explanations that help people actually make better decisions or make the team make better decisions, not just explanations that try to convince people by preying on their biases.
Yeah.
Yes?
Since you mentioned causes there, lingering questions. So earlier when you defined the term, you were talking about counterfactual, like
Right.
JJ exploitation model. Do we have to go think of that in terms of causal models, or is it just a model that cannot capture causality, but how does it behave?
So I believe, a causal or something that matches a person's causal model, that's going to be a preferred explanation. That's what you're asking. It's not clear that that's the only kind of explanation that people like, though. I'd like to highlight some work by Marco Ribeiro, this PhD student who's just graduating at UW, and he came up with a really nice system called LIME that many people are building on. And the basic idea is, suppose you've got a classifier and learn this very complicated decision boundary. The boundary is really too complicated to explain globally, so maybe what you want to do is explain it locally. This is sort of an instance-based explanation. So we could explain why did the system make this decision about that particular data point. What LIME does to generate such an explanation is it samples points around that point that it's trying to explain. And then it uses the complicated model, say the deep neural network, to generate labels for all of those points, so they don't have to be in the training set. And then it weighs them based on a distance metric. And then it learns a new model, which is an inherently interpretable model, based on these weighted data points, possibly using different features or a subset of the features. And then it uses a simple model to make the explanation. So here it's learned a nice linear boundary, and it's going to basically tell you if you're on this side, it believes this is a plus because it's on that side of the decision boundary. And that's a locally correct explanation. Globally, it makes a number of different mistakes, but in the region around that example, it does a good job. So here's an example of LIME at work. So computer vision classifier is trained to distinguish between wolves and huskies, and it actually did incredibly well on both the training set and the test set. And so natural question is, should we be trusting its predictions? Well, if you look at the LIME explanation, it's clear that the reason why it's making this distinction is because any picture that has snow in it, it thinks is a wolf. Otherwise, it thinks it's a husky. So in fact, it doesn't really seem to understand the difference between wolves and huskies nearly as well as we might have guessed. This particular example is basically using a neural network to do the computer vision, but the explanatory classifier is logistic regression. And the features, the way it works, we have to simplify this down to a different vocabulary. So the way it works is by dividing the image using an off-the-shelf image segmentation system, and then it generates nearby points by perturbing some of these regions, and then it uses the machine learning classifier to generate those, and then it generates this linear classifier based on those new data points. So this is a way, basically, of using this offline image segmentation system to create a new vocabulary, which hopefully is going to be meaningful by choosing these regions. Here's a bunch of other techniques for generating new vocabulary terms. Yeah.
How can we be sure that it's not a simple model who's predicting based on snow?
Say that again?
So how can you tell if it's this? So the predictions are made by the simple model, right?
Right.
So how can you tell if it's not just a simple model who's predicting, just identifying snow in the future?
So there's no guarantee of that. And that's, again, the fundamental conundrum. It's very, very difficult to think about how you're going to evaluate these things. And I think fundamentally the only way you can evaluate the power of these explanations is by seeing whether a person who's using the classifier with an explanation to make their decision does better than a person who's just got the classifier and doesn't get the explanation. That's really the only way to know the explanation is being useful, because any simplification is a lie, and it's not clear that it's actually.
And also, it's not that the explanation was that snow. That's like an analysis of.
That's right. I had to look at those regions and say, wow, it's actually what it's paying attention to is the regions that have snow. Yeah, it's also a distributional question. It could be, well, gosh, actually, Wilson Huskies look a lot alike, so snow is actually about as best I could do. Might make that decision, but at least it's nice to know that's what's going on. Yeah.
And is this also related to Mark's question that let's say you had a perfect distribution, very big, but the only thing that you could be perturbed locally, all you did was get examples from the neighboring leaves of the thing. So you did all the right perfect decisions, but now the only thing that remains is the snow, and that is the distribution factor, and that's okay if you have the interpretable thing. Is that okay or
So I'm not sure if I heard the whole explanation, but I think the bottom line is if the system is detecting snow, it may well be that that's actually the right thing for it to do, but it also tells you, it gives you some insights into the weaknesses of your model if the distribution is going to change. So it gives you a much better sense about when you should trust this model and when you shouldn't. So if you're just going to be trying to do it to classify animals in the zoo where there is no, where snow is not a factor, then that's a problem. If you're looking at images that are gapped off the internet, maybe it is a reasonable model to apply.
This next question is more like, let's say it had the right perfect path all the way from the way deep path with all the right things. But in your generative example, the only distinguishing factor having to do snow. And it seems like it would pick up on snow, and that's the right thing to do because it's in the right locality of the tree, right? Always been designed to also get features from the locality, what put it in that locality. The other features along with that might have been very job. I'm not sure if the explanation would be
I'm not sure if I'm understanding. The explanation is in terms of the features, which are these. Why don't we take it offline? Okay, so one of the things that I don't like so much about Lime is this approach to generating the explanatory vocabulary, which is, let's just use an off-the-shelf image classifier. So the features that get chosen really have nothing to do with the decision that fundamentally the learned model is actually using. There's some other techniques for generating features. And for the most part, they require adding some extra supervisory signal that helps train this vocabulary. One that I think is especially interesting is trying to jointly train your discriminatory model with a generative model. For example, we can jointly train the image classifier with the captioning model and try to generate explanations that way. And the problem is, you can generate, the captioning model generates an image description. The class definition is not so much necessarily relevant to the image, but is very relevant to the class distinction. So what you really want to do is generate an explanation which is both picking up on factors that are important for this class definition, but also are talking about features that appear in the image. And there's some nice work by Lisa Hendricks at Berkeley which does this. The next thing I want to do is talk about making these explanations interactive. So I said earlier, psychologists have pointed out that it's a social process and that two-way, we want to think about this as two-way conversation. I gave this example about a choice of foil. My student Gagan Benzal has been working on building an interactive system for generating explanations and thinking about what are the other kinds of dialogue actions that one can take. So we've seen that one already. Another thing you can imagine doing is restricting the explanation to a specific region of the feature space, not an instance, but the human might say, I'm only interested in what you're doing with respect to short-term municipal bonds, for example. Another question that you might want to do, a follow-up question during this explanation interaction is basically say, well, why did you believe that this was true? In which case you want to display the training examples that cause the person to think about that. Another thing you might want to do is interactively extend the feature that we're using when in the explanation. So you could teach the system a new feature and have it adjust the explanation in terms of that. And then finally, you can, if you've got a hypothesis about what the system is doing, we want to be able to update, to test that hypothesis by perturbing the input example. And then finally, we may well want to come back and debug the model. I want to give you two examples of this kind of interactive system. The first one is the one Gagan's building in computer vision, and the other one's maybe more interesting to you guys, having to do with natural language processing. So here's what Gagan's done. Again, there's a graphical user interface which is kind of hokey, and so I'm going to be using English text to illustrate what the actions are. But here we've got the system that predicts as fish. We don't want to say, well, why do you think it's a fish? It uses something like line to come back and explain what superpixels are accounting for the explanation each way. So the green superpixels are basically giving evidence of fish, and the red ones are giving evidence. This is a binary fish-dog classifier, that it's a dog. Well, that seems a little bit weird. What's going on is actually it seems to be picking up on part of the fish and saying that that looks dog-like. So we can ask, well, exactly what's going on? Which training examples caused you to believe it was a fish? And sure enough, we're getting anemones in both of the backgrounds here, so we're really worried that maybe it's recognizing anemones instead of the fish itself. So we can do a counterfactual and just edit the image a little bit and say, well, what do you think about that? Is that a fish or a dog? And it says it still thinks it's a fish. There's a couple interesting things here. One is this idea of changing a foil. In a Boolean classifier, there is only one other foil. If it's a dog versus a fish, we can edit it. So as we think about trying to extend these kinds of explanation systems to handle multi-class classifiers, it's really not clear exactly what one should do with one's explanatory model. So there's a couple different interaction styles you can imagine that we're looking at, and it's not clear which one is going to be the best. Another key thing, we've talked about finding the most relevant training examples. It's not clear how to do that. Percy Liang and a student have come up with something called influence functions, which we re-implemented, and it's just so slow, it's not really practical. Instead, what Gagan did was just use some mirror neighbor techniques on the penultimate layer of a deep neural network. So it's restricted to the neural architecture, but it works really quickly. So that's what was giving the examples a second ago. So that work is still in progress. Now what I want to do is talk about a different kind of explanations that are more aimed for a system developer. Specifically, we've been developing this in the context of looking at NLP question answering systems. And this is the work of Sherry Wu, who's co-advised by Marco and Jeff Hare. So this is her visualization system for question answering, and it's kind of an overwhelming system. So let me zoom in on different parts. You get sort of a summary model up in the upper left, and that tells you basically what your F1 score is for the system. So it gives you a sort of a high-level single number view of things. What you can do is you can look at different slices through the data where we've got Boolean predicates, and you can condition on these predicates, and we've got a large number of them predefined. So you can basically say, well, how does the system perform if there's distractors in the system? Or how does the system perform if there's a lot of co-reference going on, or long-range dependencies, or so on? Try to get a sense about where the model is working well and where it's not. You can also create new categories by exploring examples, and here we've got the statistics to give you a sense about where you've got density in the space of examples that you're looking at. And then once you've got a hypothesis about what's actually causing the errors, you can evaluate counterfactuals by editing things. So here we've got a sentence where the system gets it wrong, and we can edit the sentence and then see whether it gets it correct. So here's a single example of the system going through. So here we've looked at the performance in this particular example, and it looks like the examples that have lots of distractors are giving us some problems. We can look at similar examples by sort of clicking on these categories and very quickly look through a bunch of different instances and see these attention models for them. And we come to a hypothesis that the model seems to be having problems when you've got specifically who questions that have lots of distractors. So you can build in this little code editor. It requires code, but for those of you who can actually read the code, it's very, very simple to add in new categories. So here we've got a new category, which is who questions and has distractors. And sure enough, it looks like we're really getting a lot of errors in these situations. So then finally, we give us a hypothesis that the model is actually just picking, whenever it's got a who question, just picks the first thing that looks like a person. And so then we can go back and we can edit the example, and we can actually semi-automatically transform a set of examples by these pattern style edits to see whether or not that actually changes the accuracy. And we see actually that it does much better on these questions when we rephrase it to a what person. One other thing Sherry's been doing is focusing not just on explaining a single model, but trying to understand the difference between two models. So this comes up an awful lot when you've got a fielded model, for example, Siri, and you want to release an updated model. Before you push out the updates, you want to get a sense about what are the differences, where is it working better, and where isn't it. And I'll come back to that in a minute. So I'm going to come back to machine learning in a second, but I just want to say something about search, because AI is not just machine learning. And so a key question is, if you've got some sort of optimization or planning-based system, we need to explain that. We need to explain that too. We want to be able to trust the plans. So some people say, well, but these search algorithms are provably correct. So do we really need explanations in the case of combinatorial search? And the answer is, it's nice to have a correct algorithm, but the model that the AI system is using of the primitives is incomplete. It's an open world, and the knowledge of the goals is incomplete. So I want to give an example from a long lost collaboration with Oren. where we built a personal assistant long before Siri and so on, called the Internet Softbot. And one of the things you could ask it to do is say, how much of my storage space is being used for my photo collection? And instead of being a script-based system like Cortana and Siri are now, our system used a planning algorithm, a provably correct planning algorithm, to generate its plans. And actually came up with this plan, which is none of your storage space is being used for photos. Because it executed on a star, and it knew afterwards that there was nothing there. And in fact, it's a very efficient plan. It used very little CPU space, and it didn't have to actually go out and count things over all the directories.
I should point out that in this collaboration, Dan was in charge of the planning.
And we proved it was correct. So you think about it, it's kind of funny. You might just say, well, that's dumb. We should have just included don't delete files as a sub-goal. Problem is that there's an infinite number of those sub-goals, actually in the sense of the qualification problem. And it actually ties very naturally into common sense, but that's a whole other topic. So the same techniques that I described for machine learning apply here. You've got to have, oftentimes you want a local explanation to see what's going on. There's a vocabulary issue. You've got a complete subplan exploring a subspace. You need to generate concise explanations for that. There's FOIL-specific answers. Why did you use this action? Why didn't you achieve that sub-goal? And one way of thinking about it, I think is pretty nice, is trying to generate the minimal explanation that patches the user's partial understanding of the domain. And then finally, obviously there's lots of systems that combine planning and machine learning, in which case you need to do this kind of thing on a broader scale. Okay, so the final thing I want to talk about is maintaining trust. And I've sort of sidestepped trust all through this, and I've tried to argue that intelligibility is really important, and indeed, intelligibility, I think, combined with competence, leads to trust. But strictly speaking, you don't need to have intelligibility to get trust. It's possible to trust somebody even if you don't understand what they're doing. And again, with Oren, this came on me quite early on, where we were negotiating with an NSF program manager about our budget, and I didn't know how to do that. And I certainly didn't know what Oren was going to do, but I trusted him to do it. In fact, he did an excellent job, but that's another story. So trust basically means that the human has a model of where the AI is going to behave and operate correctly. So again, if it's intelligible and you know what it's doing and you know what the task is, you can trust it. But you might be able to trust it even if you don't know what it's doing. So interested in an environment, in a loop like this, where you've got a human AI team, the environment gives some sort of percept. The AI system makes a recommendation. The human can decide, should I just do what the agent is saying, or should I maybe dig into it, get some more information, and try to figure out what to do myself? And then you get some sort of reward based on the team performance, which is fundamentally largely about the accuracy, but also about maybe how many tasks you get done in a given time. And what you see is that over time, people build a model about where they can trust something. In fact, psychological studies have shown with any complex artifact, people build up these models about what the system is doing, where it's working well, where it's not. And that's true for AI systems, shouldn't be a surprise. So a key question, and one that Gagan Banzal's been working on in collaboration with me and H.A. Kamar, Besa Nishi, and Eric Horvitz, is what should we do if we've got an AI system and we have an update to that system? So the first thing is, first of all, obviously we like to update our system. We get a lot more training data. We can train a new classifier. That seems like a great thing. Let's push out the update. Here, for a number of domains, real-world domains, we trained on a larger training set from the same distribution, and you can see that the accuracy of the classifier goes up. What is kind of surprising is that the consistency score is oftentimes very, very low. And by the consistency score, I mean how many of the new model's mistakes were things that the old model got right. Okay? So overall, the new model is making many fewer mistakes, but it's making new mistakes that the old model didn't make. And so is that a problem? Overall, the accuracy is going up. Well, we argue that it is a problem, and that you've got a human and AI team. They can work together, especially once a person's built up a model of how the system is going. They can work better than either one of them work independently. If you update to an incompatible model, even if the performance of the machine learning goes up, the performance of the team goes down. If instead you update compatibly, then you're gonna be going up without that drop. That's the conjecture. This is what we're claiming. So we built a platform to test this using Mechanical Turk, and it allows us to vary. So basically, we're sort of a simulated, simple factory metaphorical setting where the user is given a set of objects and asked whether or not they are defective. And the thing that's nice about this is it's very easy to train people in Mechanical Turk, and we can come up with a variety of complicated tasks by adding additional features. I'm showing you a really simple example, but you can add lots of different features. Can also vary the performance of the AI system, and also vary the surface of where the AI system is making mistakes, and whether it's making deterministic mistakes or stochastic mistakes. See how quickly people build up a model of what the AI system is doing, and then what happens with updates. So the first thing is people actually build up models, and the performance of this human AI team is dependent on whether they've got a good model. If the person builds up a good model of the AI system, they tend to get a much higher score in this sort of game setting than if they've got a wrong model or they didn't build a model at all. And then similarly, also if you do updates, you see that if you do an update where you switch to compatible, so that the new errors you're making are a subset of the old errors, then performance of the team stays steady. If instead the system is making a different set of errors, then the performance of the team goes down substantially, even if you're telling the human that you've made an update. And so, a natural thing is, can we regularize, when we're doing one of these updates, can we regularize to try to make the system behave like the old model by adding in some sort of proportional term and some measure of this dissonance? How different is it from the old model on the examples the person's seeing? And what's really interesting, I think, is what happens when you do that. And this is showing the curves for many different dissonance models. The one that we like, I'm not going to go into the details of it, is this blue curve. And what you see is that the y-axis is the accuracy of the model, and the x-axis is compatibility. And this black bar, in all cases, is what the original model was, trained on a smaller amount of data. Is that by regularizing to minimize dissonance, you can oftentimes not sacrifice any accuracy at all, or very little accuracy, and build a system which is much more compatible. Although usually if you try to push that too far, then you drop down and you have accuracies which are as low or sometimes even lower than the original model. So the key question, I think, is how do you figure out what that value of lambda is so that we can get a big increase in compatibility without sacrificing the accuracy. Okay, so in conclusion, there's a whole bunch of reasons to want intelligibility. There's a basic strategy. Ideally, you use something like GAMS if you can, because you get very good performance in Intelligible. Otherwise, you need to map to a simpler model where you can map over explanations, and also we want to map back controls. So unfortunately, I didn't tell you how to map back controls because I don't know how to do that. But you can help me figure it out. And then interact with a simpler model. three key techniques for generating these simpler models. Think about this explanation not just as a generating the best explanation, but as an interactive process. And then finally, if you're updating your models, there's simple ways of minimizing the dissonance that are going to lead to higher team performance. Thanks so much.
So one concern I have about trying to make my models more intelligible is how much effort it takes to make them so, right? And I think almost all the examples I provided, they're like almost entire efforts dedicated for understanding intelligibility, as opposed to like a subsection of the work that just looks at the intelligibility of this model. So do you have any thoughts on how to lower the cost of increased intelligibility in the models you use?
What kind of cost I'm not understanding what kind of cost you're worried about. Are you worried about the speed of training the model, or are you worried about the engineering time and
Fine. Yeah.
I think that there's a number, so it depends, I think, a little bit on what kinds of models you're thinking about. But I mean, there are off-the-shelf techniques like Lime and so on that that I think you can experiment with really quite easily, or like Sherry's system, which, depending on who you're generating explanations for, if you're generating explanations for developers, and something like Sherry's system is an off-the-shelf system you can use right off the bat. So I don't think it has to take more time.
Well, for example, Sherry's system would only work if I'm interested in question answering systems that take this exact formula or like pattern, right? But in general, like if I'm building a model for a new problem, more generally, how do I try to achieve this intelligibility?
So supposing you wanted to use something like Lime, there's basically two things you need to do. You need to figure out what's the new explanatory vocabulary, and that in an ideal setting would be something that gets determined automatically, but in a text case, if you're doing text, it could be bag of words, or it could be something very simple. And then what's the explanatory model? And it could be GAMS or logistic regression, which are off-the-shelf models. So I think it's not something that takes a lot of time to adapt.
Yeah, totally. If we decide to use the use directory of first the answer there.
So I think you can do it quickly. Whether you're going to get good explanations out of it, that's unfortunately not guaranteed. Yep.
So one thing that I think you kind of touched on with the concept of the foils, and also at some other points in the talk, is the idea that like explanations can be for different purposes. I think you could also imagine more generally like goal-oriented explanations almost, right? Like if you wanted to improve the performance of the system, you're going to want a different explanation than if you wanted to make sure that you're complying with some regulation or other things like that. Have you seen sort of a lot of this come into play when making your design decisions about how to make these explanations of things, like considering different use cases for the explanation?
I haven't, and even though this is sort of an active area with lots of people working on it, I think there's very few people who've done that, and I agree with you 100%. I think that's a key thing to do. So trying to evaluate what performance task, if you've got a human AI team, how does the explanation actually help the human do oversight to the AI system? I think that's the key question. And so like our little mechanical turk platform is one way that we hope to look at that in the future. We haven't done it yet. Seems super, super important to do. Yeah.
So you touched upon intelligibility and competence leading to trust. So I guess when I think of trust about any system or even a person, it seems like I realize that everybody makes mistakes, all systems make mistakes. And I trust the ones whose mistakes are more believable in a way, like I don't know, it's a
think that's a good idea. I mean, it depends on the performance task. I think whether the mistakes do have different costs, but if they do, then it certainly does. And medical diagnosis, obviously, ordering an unnecessary test is probably not nearly as bad as missing a life-threatening disease. So there's different kinds of mistakes for sure. Seems good. Yep.
Much of the discussion seems to be sort of around two thrusts, that of attacking the features or attacking the model. And either you're bucketizing or image segmentation, or you're changing the model to be a different, more explainable model. Is there sort of a third space there that I'm not seeing that can be applied to try to simplify these or produce explanations that sort of balance more of the completeness and interpretability requirements?
I don't think so, or rather there's a third one, which is, do you want a global explanation, which is oftentimes good, or do you want an instance-specific explanation? So when I go to see the doctor, I just want that, all I really care about. I don't want the doctor to explain to me all she knows about cystic fibrosis. I just want to know about my particular case. But other than that, I don't see, not to say that it isn't there, but it seems like those are the two key things that's the model and the vocabulary.
Okay, thank you.
So with respect to interpretability, it seems like the earlier reasons that you have are kind of touch on interpretability in the sense of, as a researcher, I want to know what I can expect from my model's behavior under perturbations of the data. That's kind of like why the tree can be interpretable, because I know exactly how it's going to behave by changing data. And then the latter reasons seem to be interpretability in the sense of, I want my humans to be okay with trusting this model. And it feels like, with respect to this, I'm not saying this is right, but it feels like I don't see the incentive for giving a truthful explanation of this. It feels like you could just pander to whatever they expect to hear, and that would be possibly easier to get away with.
So I think
Right? Like,
so I think we're going to see that, first of all, especially with GDPR. I think we're going to see, systems that are designed to give, satisfying sounding explanations that absolve systems of, you see that with corporate executives too. So it's like people do it, and I'm sure we'll build AI systems that do it, although what I'm more interested in is where the explanation actually has to make the team, which is the human doing the oversight of the AI system, perform better in terms of recognizing when they should be allowing the system to go on its own, and whether they should be spending more time on the examples. And there, a bad explanation, even as convincing, is going to lower team performance.
I've got a great name for a system that panders, but maybe we should stop before we get into politics. Thanks, Dan.